Tara. This is the fourth video class from me. My name is Dr. J.B. Prasanna Kumar, working as an assistant professor in Government First Grade College, Tumkur. In the fourth video class, I want to deal with the stationary waves or standing waves on a string. In the last class, we have studied two types of waves. As you all know that, one is known as progressive wave, the other one is known as stationary wave. In the last class, we have given the difference between stationary wave and progressive wave. Let us consider the stationary wave or standing wave. The definition of stationary wave is like this. When two waves of same amplitude, same frequency and wavelength travel in opposite direction along a straight line, then the resultant wave obtained is called stationary wave or a standing wave. The stationary wave or standing wave can be represented like this. Let us consider this is the one wave, this is the one wave is moving like this, gets reflected and superimposed, formed a new type of wave is called stationary wave. In this stationary waves, we have given that the nodes, this is the node, and antinodes. Nodes, antinodes, nodes, antinodes, nodes, and antinodes. Nodes are formed like this. This is known as what you call that the definition of what you call that stationary wave. There are two types of stationary waves. One is known as transverse stationary wave. One is known as transverse stationary wave. The other one is known as longitudinal stationary wave. Let us consider the transverse stationary wave. The example for the transverse stationary wave is like this. Sonometer and Milde's experiment. Sonometer is the experiment which we have studied in PUC, and Milde's experiment which we are going to study in the same semester. That is known as what you call that transverse stationary wave. The another type of stationary wave is known as what you call that longitudinal stationary wave. The example for the longitudinal stationary wave is air column. This is the experiment which we have studied in PUC. However, in case of the example for longitudinal stationary wave is air column. In the air column, two different waves gets superimposed and formed a new type of wave called stationary wave. And I mean here the sound wave is the very good example for longitudinal stationary wave. See, in case of what you call that this transverse wave, a string is fixed at one end and gets and the disturbance produced at the one end, the same wave gets reflected and superimposed, is known as what you call that stationary transverse stationary wave. There may be the what you call that fixation of the string at both the end. Let us consider the examination. The question may be like this: theory of stationary wave on a string. That is in our syllabus. They may ask you the question like this: show that amplitude, velocity, acceleration and strain vary with position and time in case of stationary wave. Let us consider a string. This is one string of length L. L is the length of the string. When the wave, let us consider this wave is moving like this, and like this, gets reflected at this position and superimposed, formed a new type of wave called stationary wave. We know that the distance between any two consecutive nodes or the distance between any two consecutive antinodes is known as what you call that lambda by 2, half of the wavelength. However, this is the distance between this node and this node is wavelength. The next, let us consider the wave. Let me consider this wave. This wave is moving along x direction. Since it is moving along positive x direction, the expression for the wave may be like this. Y1 is equal to a sine 2 pi by lambda Vt minus x is the expression for the wave which is moving along positive x direction with the displacement y1. Y1 with the displacement of the first wave. The second wave, this is the second wave. This is the second wave. The second wave is like this, and like this. The wave which is moving along positive x direction. The wave which is moving along negative x direction. Expression for the wave which is moving along negative x direction is given by y2 is equal to a sine 2 pi by lambda Vt plus x. This is the wave which is moving along positive x direction. This is the wave which is moving along negative x direction. We know that superposition of wave is the basic principle for stationary wave. However, as a result, from the principle of superposition of wave, resultant displacement y can be written as y1 plus y2. We have substituted the equations y1 and y2 for our y. Right. Hence the equation is y is equal to 2a sine 2 pi Vt by lambda. How come this equation? 2 pi can be taken out. Vt plus Vt is 2 Vt divided by 2. 2 goes off. Hence the equation is 2a sine 2 pi Vt by lambda. Similarly, cos 2 pi x by lambda. How this expression is reduced? This expression is reduced because we know that sin c plus d is equal to 2 sin c plus d by 2 cos c minus d by 2. Finally, we can modify the above equation. We can take this cos factor here along with 2a. That is, y is equal to 2a cos 2 pi x by lambda into sin 2 pi Vt by lambda, because this expression 2a cos 2 pi x divided by lambda can be written as the resultant amplitude r. Hence the final expression is y is equal to r into sin 2 pi Vt by lambda. We can write the equation like this. y is equal to r sin 2 pi Vt by lambda, where r is equal to, this is not y, this should be r is equal to 2a cos 2 pi x by lambda is the resultant amplitude. This expression r represents, this is the expression which represents r, not y. R is known as resultant amplitude. The above equation, this equation y is equal to r sin 2 pi Vt by lambda is the expression, equation represents a harmonic wave of same period and wavelength lambda as that of two individual waves. What are those waves? y1 is equal to a sin 2 pi by lambda into Vt minus x is the one equation. The other equation is y2 is equal to a sin 2 pi by lambda Vt plus x. This resultant wave equation is similar to both the individual equations, but the resultant amplitude, there we are going to consider the amplitude as a and a. Here the resultant amplitude is 2a cos 2 pi x by lambda. 2a cos 2 pi x by lambda is the resultant amplitude. Now we want to know the expression for the velocity. The expression for the displacement is given by y is equal to 2a cos 2 pi x by lambda sin 2 pi vt by lambda. We know that the definition of the velocity is like this: rate of change of displacement. Rate of change of displacement is called rate of change of displacement is called velocity. Hence, we want to differentiate with respect to time. If you differentiate with respect to time, we can write 2a cos 2 pi x by lambda. The differentiation of sin theta is cos theta, cos 2 pi vt by lambda into the coefficient of theta is, that is, coefficient of t is 2 pi v divided by lambda. The final expression for the velocity is delta y by delta t is equal to 4 pi va by lambda, that is 2a into 2 pi v by lambda is 4 pi va by lambda into cos 2 pi x, cos 2 pi x, cos 2 pi vt by lambda, cos 2 pi vt by lambda. We have written as it is. Next, to obtain the expression for acceleration, we know that the definition for acceleration is rate of change of velocity is called acceleration. That is del square y by delta t squared. We want to differentiate the velocity equation once again. Therefore, 4 pi v by lambda written as it is, cos 2 pi x by lambda is written as it is. Differentiation of cos theta is minus sin theta minus sin 2 pi vt by lambda we are going to get. The into we have to write 2 pi vt by lambda. 2 pi vt by lambda. Here b is 2 pi vt by lambda. The coefficient of t is 2 pi v by lambda. That is, instead of writing b, we have to write 2 pi vt by lambda. Therefore, this equation is reduced to 8 pi squared v squared by lambda squared a. This b is 2 pi v by lambda. This 2 pi v by lambda can be multiplied with 4 pi v by lambda. That is 8 pi squared v squared by lambda squared into a. Cos 2 pi x by lambda sin 2 pi vt by lambda is there. If we want to reduce the same equation, then we can write the expression as del square y by delta t squared by taking minus 4 pi squared v squared by lambda squared. Here in this equation, 2a cos 2 pi x by lambda sin 2 pi vt by lambda as y. Y is the expression for displacement of the resultant wave. Displacement of the resultant wave is 2a cos 2 pi x by lambda sin 2 pi vt by lambda. Hence, the acceleration equation is del square y by delta t squared is equal to minus 4 pi squared v squared by lambda squared into y. This is the expression for what you call that acceleration. See, here also in case of velocity delta y by delta t, variation with time, x is the factor which explains the position. Delta y by delta t, del square y by delta t squared, t explains the time. Similarly, y explains the resultant displacement. In the y we have the factor x which explains the position factor. Next, we have to know the expression for strain. We know that the displacement equation, as I told you, y is equal to 2a cos 2 pi by lambda into sine 2 pi Vt by lambda we have. If we differentiate this equation with respect to x, delta y by delta x, we will get the expression for the strain, that is 2a differentiation of cos theta is minus sin theta, hence minus 2a sin 2 pi x by lambda into the coefficient of x is 2 pi by lambda sin 2 pi Vt by lambda we have. If we simplify the equation, we can write delta y by delta x 4 pi a divided by lambda into sine 2 pi x by lambda sine 2 pi Vt by lambda. This is the expression for the strain. This is the expression for the strain. Here delta y by delta x, x explains the position, t explains the time at that instant of time t. Special cases at antinode, we have the figure like this. We have the figure like this. This is the figure. This is known as antinode. These are known as nodes. These are known as antinodes. Antinode is this position, node is this position. At antinode, we can write resultant displacement y should be maximum. Y should be maximum at antinode. If you want to say y is maximum, if and only if cos 2 pi x is equal to plus or minus 1. This is the expression for resultant displacement. If cos 2 pi x divided by lambda is plus or minus 1, then the displacement y is maximum. Resultant displacement is maximum. If you want to say cos 2 pi x by lambda is plus or minus 1, then 2 pi x divided by lambda should be this angle 2 pi x divided by lambda should be either 0 or pi or 2 pi or 3 pi. Like that we can write n pi. That is, the phase difference should be 2 pi x by lambda is equal to n pi. The phase difference is integral multiple of pi. The phase difference is integral multiple of pi. Or the path difference is integral multiple of half of its wavelength. Integral multiple of half of its wavelength. The two waves are said to be at antinode. The particles of two waves are displaced at antinode. Should be, the condition should be, phase difference is integral multiple of pi, or the path difference is integral multiple of half of its wavelength. Resultant displacement is maximum. At that position, x should be 0 or lambda by 2 or 2 lambda by 2, 3 lambda by 2 and so on. And this is the equation is independent of time. I mean, this position should be independent of time. That is, while explaining the difference between progressive wave and stationary wave, we have explained. What we have explained? Distance between any two successive positions of maxima is lambda by 2. That is, distance between any two consecutive antinodes is lambda by 2. These two points of maximum displacement are called antinodes. I mean, distance between any two consecutive antinodes is lambda by 2. Further, at these points, resultant amplitude is plus or minus 2a. Resultant amplitude is plus or minus 2a. Similarly, if we simplify, particle velocity at that point at antinode, the expression for the particle velocity is plus or minus 4 pi Va by lambda into cos 2 pi Vt by lambda maximum. I mean, particle velocity is also maximum. Expression for the particle acceleration, if I substitute and simplify, del square y by delta t squared is equal to plus or minus 8 pi squared v squared by lambda squared sin 2 pi Vt by lambda is also maximum. Strain, if I substitute and simplify, the expression for the resultant expression strain, we can write delta y by delta x is 0. Finally, we can write the inference like this. At antinode, resultant amplitude is maximum. Particle velocity is maximum. Particle acceleration is maximum, but strain is minimum. That is, at antinode, resultant amplitude, velocity, acceleration are maximum, but strain is minimum. Similarly, at nodes, resultant displacement y should be minimum. Resultant displacement y is equal to 0. If and only if cos 2 pi x by lambda is 0. That is what you can write. That is 2 pi x by lambda is either pi by 2 or 3 by 2, 3 pi by 2, 5 pi by 2 or 2n plus 1 pi by 2. Phase difference is 2 pi x by lambda is equal to even multiples of half of pi. Path difference is even multiples of 1 by 4th of lambda. 1 by 4th of lambda. Next, therefore, the resultant displacement is 0 positions minimum. At positions x is equal to lambda by 4, 3 lambda by 4, 5 lambda by 4 from the origin and is independent of time. This distance between any two successive positions of minima is thus lambda by 2. We know that distance between any two successive nodes is lambda by 2. Similarly, distance between any two consecutive antinodes is also lambda by 2. Thus, distance between any two consecutive nodes is lambda by 2. Further, at this point, resultant amplitude R is equal to 0. Resultant amplitude R is equal to 0. And particle velocity is 0 minimum. Particle acceleration is also minimum. Therefore, the strain is plus or minus 4 pi a divided by lambda sin 2 pi Vt by lambda maximum. This explains that at nodes, the resultant amplitude is 0. I mean resultant amplitude, particle velocity, particle acceleration, all are minimum, but strain is maximum at node. Finally, we can compare the resultant amplitude, velocity, acceleration and strain at antinode and node. At antinode, resultant amplitude, particle velocity, acceleration are maximum, strain is minimum. At node, amplitude, velocity, acceleration of a particle is minimum, but strain is maximum. This is the inference which we have to write in examination.